This is Mick Elliott from Specifier. I'm on an impressively busy NXP Semiconductor stand, and I'm here with Brian Carlson, who is the Global Marketing Director for Automotive Processors. Now, NXP have launched two automotive processors at Embedded World. Before we get onto the product, Brian, could you just give us a little background on the development of the product and why they matter?
Sure, and thanks for visiting the NXP booth. So we actually won an award for these new product families called the S32Z and S32E. These are real-time processors, and we classify these as a new type of processor going beyond a microcontroller, providing the determinism, but also offering a lot of new features. Now what's really driving this is that the industry is going through a major revolution, really. You're seeing the vehicle architectures move to a more domain-based, where software is being consolidated by functions, and also a zonal, where we're grouping the functions in the vehicle in different zones of that vehicle. So that's driving the need for this new type of processor that handles all that real-time processing, the things that move the car, stop the car, drive the car, control the motor. These processors were optimized from the ground up to be supporting those operations, real-time operations, in a software-defined vehicle. I know that word is used a lot, but this hardware was actually designed specifically for those new types of software-defined vehicles, and we have two families, the S32E and S32Z.
So, two microprocessors launched here at Embedded World. Just give us some of the benefits and the differences for the two and how they benefit the automotive industry.
Sure, I'll start with how they're similar, because there's a lot of similarities. So both of them are 16 nanometer devices. The key thing is that this is very high performance. We're talking up to 1 gigahertz. There's 8 ARM Cortex R52 cores. Those are real-time processors. We also have a dual-core lockstep configuration for Cortex M33. That's the main processing. But what's really unique about this device is what we call core-to-pin hardware isolation or hardware virtualization, which allows us to actually isolate not only the processor, but the memory, the peripherals, and I/Os, specifically to virtual ECU. So we're moving from this hardware-centric, box-defined, ECU world to a virtual ECU world in software. So these new domain and zonal, which we talked about, are now actually software. The hardware is designed, and what's unique about it is that whole core to pin isolation all the way to the I/Os. So we have that. We have DSP, also machine learning processing capabilities, on chip up to 64 megabytes of integrated flash, which is unique, and also the ability to interface to LPDDR, DRAM, and flash. So we talk about customers have memory anxiety. As we go to software-defined vehicles, we're going to add new capabilities over time. We're going to add new enhancements. That will require new memory over time. So this allows us to go beyond a microcontroller to add that additional memory. We can support 2 gigabytes at 3.2 gigabytes per second. So very fast, very useful. But the key thing to these devices is that virtualization, that I can put separate functions, totally independent. If there's a fault in one, it doesn't impact the other. Now that's the core of both the Z and the E. Now what E does differently is it adds actuation capabilities. So when I want to actually drive the E motor, like dual motors within the car, the S32E takes to the next step to add analog, up to 5 volt support analog and digital I/Os, additional timers, which makes it ideal for smart actuation, EV control. So the Z is about safety, domain, zonal type control, and then if you need the analog capabilities or do an EV propulsion like we're showing in this demonstration here, then the S32E is ideal for those applications.
Okay, so a customer can expand the memory with using these devices, yeah?
Yeah, that's the beauty of it. That's one of the 3 premises we say this is very different than a microcontroller, because it allows them to add the expanded memory and to do it efficiently. And because we have the machine learning, we're even seeing applications where they're taking advantage of that for very large machine learning models that in today's microcontroller world for this real-time processing, it can't handle that type of, that amount of memory or do those types of advanced applications. So that accelerator is very important in real-time control, not only for DSP type algorithms, for predictive control, a lot of mathematics, matrix operations, but also the machine learning. And so it comes in handy having the external memory to support more advanced machine learning applications in these real-time control.
And these processors are suitable both for what I'd call conventional petrol-driven cars at the moment and electric vehicles as well going into the future.
Yeah, they actually can support hybrids also, so there's no limitation there. The key theme here is the isolated capabilities. It has all the interfaces to support all these types of vehicles. We do have hybrids today, so we have traditional engine control, transmission, etc. And now with the e-motor electrification, the example we're showing here is an electrification propulsion domain control, so it's all electric, but it can also support traditional ICE and hybrid configurations also.
Okay, I think you mentioned 16 nanometer process, but I think there's a roadmap forward. Can you just talk about that?
That's a great question. So today we introduced the SO2E2 and the Z2, which is the award. We won the award here for that in the hardware category. We've been talking about the SO2Z1 first of all, which will be also 16 nanometer, but it'll be half the performance and add some additional low power features. That's coming in the near future. That extends, it kind of fills the gap between the traditional microcontroller and the S32Z2 and E2. But what is exciting about this, we announced at Computex at our CEO, Kurt Sievers, announced we have a 5 nanometer test chip, which leverages the technology to take it into the future, and that gives us even more performance, more integration. So we're in 16 nanometers today, ahead of 28 nanometer traditional microcontrollers, and we've already set the stage for 5 nanometer with a test chip that's functional today. So we can run software that runs on these chips on a 5 nanometer device today, and a production 5 nanometer product line, which we haven't announced details and timing, but just for customers to know there's a very solid roadmap going into the future.
Okay, an exciting future.
Definitely. I mean, everything's moving towards software defined, and we didn't even talk about the cloud aspect, but we're doing a lot of really interesting things with the data. There's a lot of data within EVs, within propulsion control, that data for battery management. How do I know really what's the status and life of that battery? There's a lot of really interesting information that we'll be talking about and showing, building on this, that allows you to take that to the cloud to be able to do some really amazing use cases. So yes, it's taking us into the future, taking us to the cloud, and having an end-to-end secure solution.
Brian Carlson from NXP Semiconductors, thank you very much indeed.
Thank you, appreciate your time.
Thank you.